On slide number 6, we put all this knowledge to work, and we will analyze a crystal structure of a mineral called ilmenite with a formula iron, titanium, oxygen 3. We haven't talked about symmetry yet or about specific types of crystal structures, but this particular mineral has a hexagonal symmetry and it crystallizes in the so-called corundum structure, which is also found, for example, in ruby. I give you an information that both cations, both iron and titanium in this case, are in octahedral coordination environments with a coordination number of 6. And one of the things I wanted you to do is to try to determine what are the oxidation states of all atoms in this crystal structure. So both iron and titanium are known transition metals, which means that they can assume a variety of different coordination numbers to produce a charge balance formula. So the two possibilities that we can imagine are iron 2 plus and titanium 4 plus balanced by 3 oxygens 2 minus, or an iron 3 plus and titanium 3 plus balanced by 3 oxygen anions. So how do we approach this? I give you at the bottom of the page the ionic radii for iron and titanium at different oxidation states with different charges for the octahedral coordination. And I calculated for you the radius ratios. I also give you a portion of the table from the Pauling rule number 1, which shows you the preference for the different coordination polyhedra. So how do we read this? You look at the results, the radius ratios, the ratios of iron to oxygen and titanium to oxygen for the different charges, different oxidation states. And you can see that all 4 results, they fall in between 0.414 and 0.592, which classifies them all as octahedral preference. So regardless whether we would put iron 2 or iron 3 plus into this crystal structure, we would get octahedral coordination, and the same with titanium. So you can't really decide about the coordination geometry just by looking at the formula in this particular case. On the right side, I give you the values of bond lengths or bond distances between iron and oxygen and titanium and oxygen. In this crystal structure, we have 2 different distances for iron-oxygen bonds and also 2 different distances between titanium and oxygen. So in order to calculate the bond valence, we have to use the formula from the previous slide with exponent and do this for every bond. So I give you the bond valence R0 parameters, and we'll use them for iron 2 plus and titanium 4 plus. And I wanted you to try to use your calculators to do the calculations and calculate the bond valence sums for iron and titanium and check whether the bond valences that you get do agree with charges. So the results are given in green at the bottom of the slide, but I wanted you to try to do this on your own.